How vector databases search at scale, HNSW explained simply. Vector databases are designed to store and search millions, and sometimes even billions, of embeddings. Each embedding is a high-dimensional numerical representation of text, images, audio, or other data. The challenge is that similarity search across these embeddings becomes extremely expensive as data volume grows. If we try to compare a query embedding against every stored vector, the results may be accurate, but the performance is unacceptable. This brute force approach requires computing similarity scores for every vector in the database, which leads to high latency, high compute usage, and increased cost. As datasets grow, response times increase linearly, making brute force search impractical for real-world production systems. This is why vector databases rely on a different strategy called Approximate Nearest Neighbor Search, or ANN. ANN techniques do not guarantee a mathematically perfect answer, but they return results that are extremely close, while being orders of magnitude faster. In practice, this trade-off is almost always acceptable for applications like semantic search, recommendations, chatbots, and RAG pipelines. One of the most popular ANN algorithms used today is HNSW, which stands for Hierarchical Navigable Small World. HNSW is widely adopted because it provides high recall, low latency, and strong performance even at very large scale. Many modern vector databases use HNSW as their default indexing strategy. At its core, HNSW is a graph-based indexing algorithm. Each vector is represented as a node, and nodes are connected to other nearby nodes based on similarity. These connections form a graph that reflects the structure of the vector space itself. The term, small world, comes from graph theory and network science. In a small world graph, most nodes are connected to nearby neighbors, but a small number of long-range connections exist. These long-range links dramatically reduce the number of steps required to move across the graph, enabling fast navigation even at large scale. HNSW extends this idea by building multiple layers of graphs. The top layers are very sparse and contain fewer nodes, while lower layers are progressively denser. The bottom layer contains all vectors and provides the most accurate neighborhood structure. When a search query arrives, the algorithm begins at the topmost layer. It performs a greedy search, moving from node to node in the direction of increasing similarity to the query vector. Once no closer neighbor can be found at that layer, the algorithm moves down to the next layer. This process repeats layer by layer. At each level, the search becomes more refined and focused on a smaller region of the vector space. By the time the algorithm reaches the bottom layer, it is already very close to the best matching vectors. Because the search explores only a small fraction of the graph, the number of similarity computations is drastically reduced. This allows HNSW to scale efficiently to millions or even billions of vectors while still delivering low-latency responses suitable for real-time applications. Another key advantage of HNSW is that it is highly tunable. Parameters such as EF_search control how many candidate nodes are explored during a search. Increasing this value improves accuracy and recall, while decreasing it improves speed and reduces latency. Similarly, EF_construction determines how well the graph is built during indexing. Higher values create a more connected graph with better search quality, at the cost of additional indexing time and memory usage. In modern Gen AI systems, HNSW is used extensively inside vector databases. It enables fast semantic search, powers recommendation engines, and plays a critical role in retrieval-augmented generation workflows where low latency and high relevance are essential. Key takeaways: HNSW allows vector databases to search at scale by organizing embeddings into a hierarchical, navigable graph structure. By avoiding brute force comparisons and intelligently navigating the vector space, HNSW delivers fast, accurate, and scalable similarity search. This makes it a foundational algorithm behind modern Gen AI applications, vector databases, and RAG systems. In the next video, we'll explore how HNSW parameters impact performance and how to tune them for different workloads. If you found this video helpful, like and subscribe for more Gen AI deep dives. Thanks for watching.